All right, number 31 from section 3.1. All right, what page is this on? Page 169. All right, 31. The directions say to locate the absolute extrema of the function on the closed interval. When we're on a closed interval, extreme values can occur at the endpoints or at critical numbers. Okay? And remember what critical numbers are. Critical numbers are x coordinates that make the derivative equal 0 or the derivative not exist. So on 31, we've got y equals 3 minus the absolute value of t minus 3. Whenever you have an absolute value in a function, aren't you going to have a cusp? Because it's going to be v-shaped, right? Okay, so we know we have a cusp when it makes the v. So that happens when the expression inside the absolute value is 0. So we're going to have that when t equals 3. Now, also, I hope we can figure out that it's going to be, this is going to be linear, right? It's not any weird absolute value. So it's going to be linear. The derivatives of lines exist everywhere except, well, the v. That's not really a line, but since we've got the v for the absolute value sign. And otherwise, the derivative exists, right? But it doesn't equal 0 unless it's a horizontal line. Okay? So from -1 to 5, then we've got t equals 3 as our only critical number. So we need to test our critical number, and we need to test each endpoint. The larger of those three numbers we get is the maximum. The smallest one is the minimum. So I find the value of the function when t equals 3, the value of the function when t equals -1, and the value of the function when t equals 5. Well, 3 is the largest value I get from those 3 points, so that's the absolute maximum. And -1 is the smallest, is the least that I get. That's absolute minimum. As long as you're allowed a calculator, go ahead and graph that if you want to. Verify. Graph contribute, because how often do you take the trouble to actually put the closed interval in there as your window and make it from -1 to 5? Sometimes you trick yourself. All right, what else from this section that we haven't gone over yet? All right, on 23, same direction. Locate the absolute extrema of the function on the closed interval. Now, in 23, they give us f of x is x cubed minus 3 halves x squared. This is a simple problem. Nothing weird going on. Don't worry about absolute values. This is just straightforward. Do you know what how extreme values work? Okay? And again, where can extreme values occur? If there's no closed interval, we just worry about critical numbers. Okay? If there were not a closed interval, all we do is find the critical numbers, and if there's a maximum or a minimum, it occurs at one of those critical numbers. But for now, they're giving us closed intervals. So we've got to test the endpoints as well. And here's why you can't forget to test the endpoint. If you have a function just like that, give it a closed interval, and the max and the min occur at the endpoints, don't they? Okay? So you can't forget those when you have them. All right, so let's find the derivative. So f prime of x is going to be 3x squared minus 3x. And then let's find the critical number. So critical numbers occur when f prime of x equals 0 or f prime of x does not exist. Well, this is how f prime of x does exist. Okay? Derivatives of polynomials exist everywhere. And then once you get the derivative, it's a polynomial. It exists everywhere. So f prime of x does exist. So we can still find critical numbers, though, from where the derivative equals 0. So take 3x squared minus 3x and set it equal to 0. Now, if I'd have really been thinking, I would have gone ahead and factored this up here, right? I just didn't think to. But I know that I want my derivative factored as much as I can factor to find critical numbers. So 3x times x minus 1 equals 0. And from there, I use the zero product property to realize that 0 and 1 are critical numbers. Something we have to watch out for is they decided to give us this closed interval from -1 to 2. Are both of our critical numbers in that interval from -1 to 2? They are. All right, but watch out for it, though, right? Because if we got a critical number that's outside of that interval, then we need to ignore it. So 0 and 1 are our critical numbers. So that means I need to find the value of the function at 0, the value of the function at 1, the value of the function at a, -1, the value of the function at b, 2. The largest of those values is the absolute max. The smallest of those values is the absolute min. So I found f of 0, and that's f. It's not f prime of, it's f of 0. So I found f of 1, then I found f of -1, and I found f of 2. Does all that make sense? All right, then, well, let's see. It looks like 2 is the largest of those values, and looks like -5/2 is the smallest. Now, there are different ways of writing what your extreme values are. And I won't always do it this way, but this is really my favorite way. To say the absolute value, the absolute max is f of 2, which equals 2. I like doing it that way because it tells the grader everything they could possibly want to know. It tells them that that is the largest value, and it also tells them it happens for that x coordinate. Okay? I like doing it that way. Then the absolute min is f of -1. So I know that the minimum value occurs when x equals -1, and then I tell them what that minimum value is. It's -5/2. Okay? So it's very similar to just giving them a point. 2, 2 is where the absolute max occurs. -1, -5/2 is the point where the absolute min occurs. Remember, the extreme values are actually the y coordinates. Pay attention to the directions. If you're not sure if they're asking you for the value or just the x coordinate where it happens, give them both. Okay? Give them both. All that makes sense? All right, what else? 33. All right, same directions. They give us f of x equals the cosine of pi x, and they give us a closed interval from 0 to 1/6. That's not a very big interval. From 0 to 1/6. So we know where the extrema occur, at the end points or at a critical number. So they've given us the end points, so we need to find critical numbers. To find critical numbers, we need the derivative. So f prime of x equals, well, the derivative of the cosine of u is -sine of u times the derivative of u. So the derivative of the cosine of pi x is -sine of pi x times the derivative of pi x. So negative sine of pi x times, and then the derivative of pi x is pi. Just like the derivative of 4x would be 4, the derivative of pi x is pi. And then I didn't do a whole lot of simplifying there, did I? So that's my derivative in as simple a form as I can get it. So critical numbers occur when f prime of x equals 0 or f prime of x does not exist. Well, the sine of pi x exists. Therefore, negative pi times the sine of pi x exists. So the derivative always exists because the sine always exists. Okay? So, no critical numbers there. You'll write that. Because like we talked about yesterday, you know, when things that might matter end up not mattering, you still need to address it. You don't want the AP grader to think you just didn't know you needed to worry about where the derivative does not exist. Okay? All right, so let's find where the derivative equals 0. So negative pi times the sine of pi x equals 0. Divide both sides by negative pi, and I get the sine of pi x equals 0. Well, on the interval from 0 to pi, or from 0 to 1 over 6, 0 to 1/6, when is sine going to equal 0? Only when theta equals 0. So set the theta, pi x, equal to 0. Just unit circle. Okay? When is the sine equal to 0? When the theta is 0. All right? No need to go around the unit circle more than once. You're just going from 0 to 1/6. Okay? So 0 is the only critical number. Now, 0 is also an end point. So we've really only got to test 0 and 1/6, don't we? Okay? I thought there would be more things to test. And if you notice, this happens every now and then where one of the critical numbers is one of the end points. I don't really know if they're doing that on purpose or not, but it sure seems to happen a lot. Okay? So I need to test 0, and I need to test 1/6. So I go back to the original function, not the derivative, put a 0 in for x, so that'd be the cosine of 0, which is 1, so f of 0 equals 1. Put in a 1/6 for x, so that's the cosine of pi over 6, which is radical 3 over 2. Well, 1 is bigger than radical 3 over 2. And look, I know that without doing a whole lot of figuring, don't I? Because radical 3 over 2, square root of 3 is smaller than 2, right? Square root of 4 is 2, so square root of 3 is a little bit smaller than 2. Well, something smaller than 2 over 2 is something smaller than 1, so I know that 1's bigger than it. So even without using a calculator or anything else, I know that 1's the bigger one and radical 3 over 2 is the smaller one. So the absolute max is f of 0 equals 1. The absolute min, f of 1/6 equals radical 3 over 2. All right, I want to take a look at number 53. The directions for 53 say this. Graph a function on the interval from -2 to 5 having the given characteristics. We're supposed to have an absolute maximum at x equals -2, an absolute minimum at x equals 1, and a relative maximum at x equals 3. So when I did this, all right, the first thing they tell me is absolute maximum at x equals -2. So I went to x equals -2, and I just picked a place to make that's the absolute maximum. I can never, the rest of the graph has to be lower than that. All right? The absolute minimum is at x equals 1. So I went to x equals 1, and I chose, and I just made it up. I don't really know how far up or down those points should be, do I? And then there's a relative maximum at x equals 3. So it needed to be bigger than the bottom one down there, but less than the top one there, so I just picked there. I do not know those values exactly. I know the x coordinates exactly. I don't know the y coordinates exactly. Then I just draw something to make it fit, okay? So you can see what I drew to make it fit. Don't get too fancy, because if you start doing all this mess, aren't you putting other relative maximums and minimums into your problem? Well, they didn't tell you there are any others. So don't make any others, okay? So, in effect, I had this, but don't make everything lines. But that's the way it's got to work, right? And then I just fancied it up a little bit. I just curved it and connected the dots. Okay? 53 makes sense? All right, 54, similar problem. We have a relative minimum at x equals -1. So I'll put that on there. We have a critical number at x equals 0, but no extrema. I have no idea what that means. Something weird's going to happen at x equals 0. Then we have an absolute maximum at x equals 2, so I'll put that up there, and an absolute minimum at x equals -5. So this one over here was a relative, well, I don't even remember what, relative min, so I've got to make the absolute min lower than that. So, again, I know I'm going to connect the dots, right? So in its simplest form, I could do that. But then, again, don't make everything lines, because how often do we run into functions that are just connected line segments? Almost never. Okay. So, so I'm going to curve it up. I'm going to, curve it, But I need to. What in the world? I have a critical number there, but no extreme. Critical number there. So either the derivative equals 0 or the derivative does not exist. If the derivative equals 0, that's a horizontal tangent line. If the derivative does not exist, what kind of a line has a slope that does not exist? Vertical. So I need to make either a horizontal tangent line or a vertical tangent line at x equals 0. Well, the easiest one to make, considering I'm trying to go from that point to that point, is a vertical one. Kind of like a cubic function has a vertical tangent line there at the, I don't even know what to call that. Okay? At the spot where it changes. Later on we'll call that, well, I know what to call it. I don't know if you know what to call it, so I'll just shut up now. All right? I could try to make a horizontal tangent line. I don't know if I can. Kind of like that. I missed the 0 a little bit, but I could try that. Vertical is what's more likely to happen. Okay? So that's what's going on right there. I'm attempting to make a vertical tangent line right there. All right? All right, any others from that section? All right, let's take a look at Rolle's theorem and mean value theorem then. Number 13. So I'm on page 176. All right, 13 says, determine whether Rolle's theorem can be applied to f on the closed interval from a to b. If Rolle's theorem can be applied, find all values of c in the open interval from a to b such that f prime of c equals 0. So, does Rolle's theorem apply? Well, remember the conditions necessary for Rolle's theorem to apply. You have to have a function that's continuous. You have to have a function differentiable. And then you have to have a closed interval, and at the values of the function at the end points of the interval have to be equal. F of A has to equal F of B. Okay? So f of x is a polynomial function. They don't have it written as a polynomial, but it's 3 binomials multiplied together. Once I multiply that out, isn't that going to be a polynomial? Polynomials are continuous everywhere. They are differentiable everywhere. So f is a polynomial function, so it is continuous. and differentiable for all real numbers. So I don't care what closed interval they give me, this one fits the bill. What I don't know is, does f of a equal f of b? Well, a is 1, b is 3. If I plug a 1 in here, what do I get? 0, because that first factor becomes 0. 0 times whatever else, it's 0. If I plug a 3 in here, what do I get? 0, because that last factor is 0. So f of 1 does equal f of 3, and I wish I'd written out that they both equal 0. So equals 0. That means Rolle's theorem does apply. So what we're supposed to do then, the conclusion of Rolle's theorem is that if your function is continuous and it's differentiable and the values at the endpoints are equal, then there's at least one number where the derivative equals 0. There's at least one x coordinate where the derivative equals 0. And we now know to call it wherever the x coordinate equals 0, that's a critical number. So there's at least one critical number where the derivative equals 0. So instead of using the product rule, it seemed easier to me to just multiply that out and make it into a polynomial. Then I took the derivative. So those first few lines are just multiplying it all out, combining like terms. And so f of x equals x cubed minus 6x squared plus 11x minus 6. And then taking the derivative of that's easy. So that would be 3x squared minus 12x plus 11 for my derivative. Rolle's theorem guarantees that, well, since this function meets all the conditions of Rolle's theorem, then Rolle's theorem guarantees there's at least one x coordinate between 1 and 3 where the derivative equals 0. So we found the derivative, set it equal to 0, and let's see what we get. So remember that a is the coefficient of x squared, b is the coefficient of x, c is the constant, x equals negative b plus or minus square root of b squared minus 4ac. All of that is over 2a. So I'll work it down to here. Now, from 1 to 3, that's a pretty small interval. So I'm not real confident that both of those numbers are going to be in the interval from 1 to 3, but they are. And if you don't trust me, use your calculator, punch them in, and you'll see that they are. So if I've got 6 minus square root of 3, and then divide that by 3, that's between 1 and 3. If I've got 6 plus square root of 3, and then divide that by 3, that's between 1 and 3. So they both are legitimate answers. 21. All right, let's see. We're still doing the same thing? Yep. All right, so we've got 6x over pi minus 4 times the sine squared of x as our function. Does Rolle's theorem apply? Well, let's see. This is the same thing as 6 over pi x. So that's just a linear function, isn't it? That part is. That's continuous. That's differentiable everywhere. This part, right, I know that the sine function is continuous and differentiable. If I square it, it's still continuous and differentiable. If I multiply it by 4, it's still continuous and differentiable. So we had a theorem at some point way back when that said that when you add together functions that are continuous you get a continuous function. And when you add together functions that are differentiable, you get a differentiable function. So, as odd as it looks, that function is both continuous and differentiable everywhere. So then we need to see whether or not the endpoints are equal. And boy, I'm sure hoping that they're not, but it looks like they are. Let's see. I'm sure I did this on my calculator. Let's see. Oh, I'm not used to this new operating system. So let's see. If I do 6x divided by pi, do I need parentheses in front of my? Then I'll do the sine of x squared. Okay. Let's evaluate that. I think I'll just make a table. Let's evaluate that for 0, and let's evaluate it for pi over 6. All right, so the endpoints are equal because the value each time is 0. All right. Then we take the derivative. Well, the derivative of 6x over pi, again, it's like 6 over pi times x. So the derivative of 4x is 4, so the derivative of 6 over pi x is 6 over pi, minus, then I need to use the chain rule. Think of that as 4u squared. So it'll be 2 times 4, u, subtract 1 from the exponent, times the derivative of u. So 2 times 4, u, subtract 1 from the exponent, times the derivative of u. Everybody follow me on the chain rule there? So, end up with this. So, let's see. So I'll put in 6 over pi minus 8 sine of x cosine of x. Better make sure I'm in radian, which I am. Let's see, let's turn this off. All right, and let's find the zeros of that between 0 and pi over 6. So it looks like we've got one right about here. Okay, and we'll try to narrow in on that. So second calc, 0. I'll let 0 be my left bound. And then just scroll it over until you're on the other side of the x-axis. I'll let that be my right bound. Back it up just a tad there. And so 0.2488837 is the x-coordinate where that derivative equals 0. There's ways to do it without graphing. That's the way I always remember to find a 0. I just graph it and then do that 0 thing. With the new operating system, I could probably figure out how to do it without graphing it first, but considering I still want Windows XP, I'm not too, I don't like new operating systems. I have to learn new things. All right. Does that help? All right, we got time for another one. $39. Let's see. Determine whether the mean value theorem. All right, so mean value theorem. the endpoints don't have to be equal to each other anymore, do they? We still need a function that's continuous and differentiable, but now the endpoints don't have to be equal. And if it can be applied, then we'll find all values of C such that f prime of C equals f of B minus f of A over B minus A. All right, f of x equals x squared. That's a polynomial, so it is continuous. It is differentiable. Endpoints don't matter. So the mean value theorem does apply. All right. Find the derivative. Well, the derivative of x squared is 2x, so f prime of x equals 2x. The conclusion of the mean value theorem is this, that there's at least one C that makes this happen. F prime of C equals f of B minus f of A over B minus A. Like we talked about yesterday, f of B minus f of A, that's y2 minus y1. B minus A, that's x2 minus x1. So there's at least one place where the slope of the tangent, that's f prime of x, equals the slope of the secant that connects the endpoints. Or the instantaneous rate of change equals the average rate of change. Or the instantaneous velocity equals the average velocity. So f prime of C, I use x instead of C. So f prime of x, 2x, has to equal f of B. Well, look, there's B, so f of 1. F is x squared, so 1 squared, minus f of A. Well, A is negative 2, so f of negative 2, negative 2 squared, over B again, 1, minus A again, negative 2. All right, you with me? Okay, we got it beat now. So I'll get negative 3 over 3 on the right. So negative 3 over 3 is a negative 1. So 2x equals negative 1. So x equals a negative 1/2. So that C we were looking for is negative 1/2. All right. Anything else? 40 what? 43. Let's see. Mean value theorem again? Yeah. So let's see if it applies. All right. That's a radical function. Radical functions are good. They're continuous and differentiable as long as we don't get a negative under that square root sign. And on the interval from negative 7 to 2, we don't. We get a 0 when x equals 2, but we don't get a negative. So, unfortunately, f is continuous, and it's differentiable on the interval. Wish they'd have gone to like 3, and then we could have said mean value theorem does not apply, and we could have gone on to the next problem. All right, so that means, yeah. Yeah, if it doesn't apply, you just tell why it doesn't apply, and you move to the next problem. Okay? So we need to find the derivative, use the chain rule. You don't have to rewrite it, but you sure have to think of f of x as being 2 minus x to the 1/2 so that you can chain rule it. So that would be exponent times the coefficient of the parentheses, using the general power rule, be 1/2, 2 minus x, subtract 1 from the original exponent, so the new exponent's a negative 1/2, and then times the derivative of u, times the derivative of the inner function, times the derivative of the parentheses. Well, the derivative of 2 minus x is negative 1. That's how I got that. So I've got a negative factor. I've got a 1 in the top. I got a 2 in the bottom. So I just took care of the negative 1. I took care of the 1/2, didn't I? Now that 2 minus x to the negative 1/2, move that factor to the bottom because it is a factor, and make the exponent a positive 1/2. And instead of doing an exponent of positive 1/2, I might as well make a square root. All right. We okay on the derivative? All right. That's the conclusion of the mean value theorem. So I got to find the x-coordinate that makes that conclusion work. So f prime of C F prime of x for me, we just found it, that's that. F of b, well, b is 2, so the square root of 2 minus 2, minus f of a. A is negative 7, so the square root of 2 minus negative 7, over b, 2, minus a, negative 7. That's how I get that. And then I solve it. Simplify. I get a 0 minus 3 over here. 0 minus back to negative 3. Negative 3 over 9. Negative 1/3. Pick up negative 1/3. Right. Add to the left. At this point, notice how I've got a negative left side and a negative right side. I just multiply each side by negative 1 to be done with the negative. So multiply each side by negative 1 to be done with the negative. Then do cross product. So 2 times square root of minus x times 1 is 2 square root of minus x. 1 times 3 is 3. Then I multiply 2. Side. Then 2 to both sides. Then I divide both sides by negative. I think we'll stop here. Now, just because you see me work a problem doesn't mean you're able to work a problem. So if I've worked problems you haven't got to do it. If I've worked problems you couldn't work before, you need to try these things. Okay? Because, look, you know that, right? It's a big difference. Watching somebody else do it. So make sure